All right, on our warm-up, the first one that I picked is our secant of 2x cubed minus 4. And the reason that I picked this is because sometimes we're missing the inside of this as we go to do our derivative. So a lot of us can tell me that this derivative of secant x is secant tangent. However, when the inside, when we're looking at a chain rule type of problem, as you do translate the derivative of secant x being secant tangent, that whatever is inside here has to also show up inside both of those functions in your derivative. So this would become secant of 2x cubed minus 4 tangent of 2x cubed minus 4, then times the derivative of the inside, which would be 6x squared. And cleaning that up, we probably could just move that 6x squared to the front. Okay, and on the next one, I picked this one for a couple of reasons. One of those is we probably would attack this initially as our product rule, but I want to show us also a second option. So if I were to attack this as my product rule, I would do first, and actually first I would probably have rewritten this as 8x to the fourth times x to the 1/2. First times the derivative of the second, which would be 1/2 x to the negative 1/2. Plus second times the derivative of the first. Okay, and the cleaning up in this one is a little bit ugly, and typically we would use that move that x to the 1/2 down to the bottom of our fraction, and a lot of us would probably clean this up. 8 times 1/2 is 4x to the fourth over the square root of x plus 32x to the third square root of x. We would want to get a common denominator on that. So I'd multiply this by square root of x top and bottom. That would give me x right here times the x that is already there is an x to the fourth. So that would give me common terms in the top. 4 times 32 would be 36. X to the fourth over the square common denominator square root of x. Although that looks great, a lot of times we also would want to maybe get, so we only have one x in that. And so I just want to show you a second option of how we could attack this same problem. And that goes from taking the rewritten version up here, 8x to the fourth x squared. If they have the same base, I really can put those together. And remember, the rule if they have the same base is that we can add the exponents. So this would have looked like 8x to the 4 times a half, which would be 4 halves, or 4.5, or 9 halves. And then it becomes a very simple problem that I can just do my power rule. 9 halves times 8 would be 36. Subtract 1 from 9 halves would be 7 halves. And we can actually just leave it like that, 36x to the 7 halves, which is the same thing you're seeing on the other one, 36x to the fourth over x squared, because we would have x to the fourth minus x to the 1/2. 4 minus a half is 7 halves. All right, so continuing on within our implicit differentiation notes, 4.2, day 2. Kind of expanding what we did, now that we know how to use implicit differentiation, we can use that to do something like find the equation of the tangent and normal lines to a function, x squared minus xy plus y squared equals 7, and we want to find those lines at -1, 2. So if I do my implicit differentiation here, I would have 2x, and then we would do our product rule for the next, which would be first times the derivative of the second, -x times y prime, plus second, which is y, times the derivative of the first, which would be -1, plus the derivative of y squared would be 2y, y prime, and derivative of 7 would be 0. So gather all my terms that have the y prime, -x y prime plus 2y y prime, and I'm going to move the -1y over, move the 2x over, take out my GCF, and divide to get y prime by itself. Okay, so that gives me my derivative. And remember, as we are writing the equation of a tangent line, we need two things. We need a point, which they gave us, and we need the slope, which comes from the derivative. Well, that's what I'm working on right now. I'm working on my derivative, and I want to specifically evaluate this derivative at the point given, so -1, 2. So now, again, I just need to be careful that I put my x's and y's into the equation in the right place. So replace y with 2, replace x with -1. And cleaning that up, 2 plus 2 is 4, 1 plus 4 is 5, and it looks like we get a slope of 4/5 at that point. So our tangent line would be y minus 2 equals 4/5 x plus 1. And our normal line, use our opposite reciprocal slope, y minus 2 equals -5/4 x plus 1. All right, and then the next thing that we're going to get into is our second derivatives using implicit differentiation. And the little trick to our second derivatives is at different points throughout, we are going to have to look to sub back in things that are equal, so that when we get done, we don't have like a y prime left inside of our second derivative or anything like that. So start with your first derivative like normal. So as we do the derivative of our first derivative, let's see, 3 times 2 is 6x squared. And then we would have 6 y to the first y prime equals 0. Solving for y prime, I would subtract 6x squared, divide by -6y. And we find out that y prime equals, and my -6's cross off, I get x squared over y. Then I take that and I do my derivative of y prime. Well, the derivative of y prime becomes y double prime. And then I do my quotient rule. My quotient rule says bottom times the derivative of the top, which would be 2x, minus top, times the derivative of the bottom. Derivative of y is y prime over the bottom squared. And this is where I'm going to do a little cleaning up, but also we're going to look to sub in for y prime what y prime equals. So again, we don't have a y prime in our answer, and then it'll be all just plain x's and y's. So y double prime equals 2xy minus x squared, and then replace y prime with x squared over y. Okay. Now, to clean this one up, I would get rid of that fraction. And there's a couple different ways you could do this. You could get a common denominator in the numerator, add those together, and then multiply by the reciprocal of the bottom. I could also just multiply this fraction by 1, and the 1 I would pick is whatever the denominator is. So if I were to multiply this fraction by y over y, again, I picked y because that's the denominator of this fraction. That would have to get distributed to both terms here. And when I take y times the y in that second term, those are going to cancel. So doing that, I would get 2xy squared minus, and then again, my y here and my y here cancel as I do that second distributing through, which would give me just an x to the 4th, x squared times x squared, and in the bottom, a y cubed. I think that's probably the easiest way to attack cleaning that one up with the fraction. All right. In this last one, it says identify all ordered pairs. And so I see right here, first of all, it says identify all ordered pairs. So I know my answer, it needs to be in the format of x comma y, where that function has, and then the next thing I need to pick out for my directions is the important part that says horizontal tangents. Remember that horizontal tangents are going to happen where the zeros of my derivative are located. And that's where I find my horizontal tangents, is I'm going to find my derivative and set it equal to 0 to locate. So job number 1, find the derivative. So let's go through and differentiate using our implicit differentiation. First function, x minus 5 squared, chain rule. So I would do power rule on the outside, leave the inside alone, times the derivative of the inside. Well, times the derivative of x minus 5 would be times 1, which is not going to change anything. Second, again, I do my chain rule, so derivative of the outside, leave the inside alone, times the derivative of the inside. And this time, the derivative of y minus 3 is going to be y prime. Derivative of 25 is 0. And then I need to get y prime by itself, so I can add. So I just distributed this 2 through here. Subtract that 2x. Again, I can distribute that through there. So I would have 10 minus 2x over here, and divide by 2y minus 6, giving me y prime equals 10 minus 2x over 2y minus 6. We could actually have left that 2 out of there. All of those are divisible by 2, so I could simplify this down to 5 minus x over y minus 3. So now I want to find the zeros of my derivative. So I'm going to take that derivative and set it equal to 0. Okay, well, if a fraction is going to equal 0, it's going to be the numerator. Solve for x, and I find out that x equals 5. So I know now that in my ordered pair, it's going to be 5 comma something, and that something comes from when I plug 5 into the original function. So I go back up to my original function, and I plug that 5 in. And so as I do that, I plug 5 in for x. And we're going to solve for y. Well, 5 minus 5 is 0, squared is 0. So then we're looking at y minus 3, quantity squared equals 25. And as I solve this, when I square root, this is where I got to remember my algebra. Square rooting a number means I get both the plus and the minus of that. So I would actually get 2 answers here. Y minus 3 equals 5, and y minus 3 equals negative 5. So we get y equals 8, and y equals negative 2. So we get 2 options, 5 comma 8, and 5 comma negative 2. All right, and our assignment is going to be on page 13, and you have the rest of the hour to work on that. And tomorrow we will come back and review implicit differentiation one more time.